Yeah, so welcome to my presentation. My name is Christoph Jung, and I present joint work with Carsten Lutz from Bremen and Hadrien Pulcini and Wolter from the University of Liverpool. The topic of our paper is the separability problem, and the separability problem is defined as follows. So you have as an input a knowledge base and a set of positive examples and a set of negative examples. And the question is whether there is a separator between the positive and the negative examples. To make this a little bit more concrete, I have a small example. So assume we have a knowledge base, and here it's some geopolitical knowledge base, and the positive examples are just Athens and Berlin, and the negative examples are Washington, D.C. and Bologna, so those are constants. And well, those the positive and the negative examples in this case can be separated by an EL concept, namely by the EL concept capital and a capital that is located in Europe, because both the positive examples satisfy this concept and none of the negative examples satisfy this concept. So we are interested in a logical separator. In machine learning, people maybe would call it a classifier, right? The separability problem has many applications, in particular concept learning, query reverse engineering, query by example, and also it has applications in referring expressions and entity comparison, for example, in RDF graphs. Let me just say that for concept learning, we have already seen an example. So we have learned that Athens and Berlin have something in common, namely that they are European capitals. Okay, throughout this talk, I will be making the open world assumption. I know this is common in the DL community, but still I want to stress it because there has also been a lot of research on this separability problem in the database community where they do the closed world assumption. Okay, so the separability problem is not well defined yet, and it has many kind of dimensions. And I want to discuss now a couple of dimensions of the separability problem. First of all, I want to define it really what it is. And there are actually two versions, namely the weak and the strong separability problem. And in both cases, we require that this logical separator, phi, is entailed for all the positive examples. Okay. And then in the weak case, we require that the logical separator is not entailed at all negative examples, while in the strong case, we require that the negation of the separating formula is entailed for all negative examples. Of course, the strong case is much stronger than the weak, and but in closed world, they coincide. I mean, in the closed world, there's no difference between those two. Another dimension is the language of the separating formula. There you actually have the free choice between first order, some formula and some decidable fragment of first order logic, some description logic concept, even some query language such as conjunctive queries. In this paper, we will have that the ontology language will always be the same as the separator language, separating language. Yeah. But this is not necessarily true. Okay, another dimension is whether you admit helper symbols in the separating formula. And if you do so, then this would be projective. And if you don't, then this is the non-projective case. And this really makes a difference. So I have this very small example. So A and B, so we have an empty ontology, and this is the database. Then it's easy to see that A and B are actually bisimilar. So there is no ALC concept that separates them. But if you admit symbols that are not in the database, for example, a unary predicate P, then A and B are separable by this concept. What is new here is that we add an additional dimension, namely we add an additional input, which is a signature restriction on the separating formula. And the idea is that you want to have this because you would like to direct somehow the separating formula towards a certain criteria or a certain topic, for example. Yeah? Very similar to what has been done in modularity. And one example, one instance could be that you want to forbid race or gender to be involved in the separating concept. And the topic of this paper is to find out what is the impact of the signature restriction, because without signature restriction we have studied the separability problem in previous work, HK 2019, and also in next week there will be a paper presented about this. And I mean, I want to give you just a rough overview. So one kind of impact can be measured in the computational complexity. And in this paper, so this is the gray column, are the results that we establish here. So you can see that always, if you admit signature restriction, the problem becomes harder, sometimes even undecidable. And okay, this is interesting. But also what is interesting is that there's kind of a natural explanation, and the reason, somehow an underlying reason why this complexity jumps. And for this, you have to look at the problem and try to characterize it. And it turns out that the nature of the problem changes. So without a signature in the input, projective weak separability is more or less related to rooted conjunctive query answering. And strong separability is related to satisfiability problem. If we add the additional signature, then the problem changes somehow its nature. So the separability problem is then very close to conservative extensions or to interpolation existence. That will go into the details a little bit more in the next couple of slides. Another thing that changes, that is also in the paper that I will not talk so much about, is that one can also look at the different separating languages. So let's say we have an ALCI ontology and we want to know whether we can separate with ALCI concepts or with first order concepts or with UCQs, and whether this makes actually a difference. And there are examples. So also here the signature has an influence, for example, in the strong separability case, ALCI, strong separability, and FO separability are the same, and this is not the case for the case with an additional signature. But yeah, I refer you to the paper for more details. What I want to do is I want to talk about those two relations, so to conservative extensions and to interpolation existence. And I will start with the weak separability case and the relation to conservative extensions. Okay, so let us start with the description logic ALCI. So this is the ontology language and also the separating language. And it's known that conservative extensions are 2x time complete. And I give you a rough idea why there is a relationship between conservative extensions and the separability. So for conservative extensions, you have an ontology O2 that is an extension of O1. So you add some new axioms. And let's say we have a concept that is formulated in the signature of the first ontology, O1. Then two things are equivalent. So this concept is a witness for non-conservativity of O2 over O1. That means that the concept is unsatisfiable with respect to the second ontology, but it was satisfiable with respect to the first one. Then this is equivalent to that the negation of the concept is a separating concept in a slightly modified knowledge base. Namely, you take the first ontology and the added axioms you relativize to a fresh concept named A. Then this unsatisfiability can be detected because if you have an instance of A, then not C will be entailed because C is not satisfiable. If you have a non-instance of A, then not C will not be entailed, so not C is a separating concept. And this gives you a 2x time lower bound, and an upper bound can also be established. We do this by giving a characterization and then use tree automata. We have also looked at other description logic, well, ontology language, namely ALC, OIF, and the guarded fragment. And the reason is that for those logics, the conservative extensions are undecidable. Unfortunately, this very simple proof idea doesn't work because the relativization is not applicable for ALC, OIF because we have nominals, and for the guarded fragment because conservative extensions are defined in terms of sentences and not in terms of formulas, open formulas. But still, we could adapt the undecidability proofs and show that projective and non-projective weak separability are undecidable for every logic that contains either ALC or OIF or the guarded fragment, even with free variables. Okay, then I also would like to talk about strong separability, and in this case, there's a relation to interpolation, and also this can be shown actually quite easily. So if we have some formula and a knowledge base, then the formula phi strongly separates A and B in this knowledge base. Well, this is just a definition. K implies phi of A and K implies not phi of B. You can rewrite this a little bit by just rewriting the knowledge base as a first order formula and make A a free variable. And then this is equivalent to this formula. Phi sigma A implies phi and phi implies not sigma B. And this is actually just the definition of phi being an interpolant for those two formulas, phi sigma A and not phi sigma B. So actually we have given a reduction of strong separability to the existence of some interpolant. Now, if the logic has the correct interpolation property, so that means that then the interpolant exists if the two formulas entail each other, so the first entails the second, then actually this gives us a reduction to validity in L, provided that these formulas phi sigma A and phi sigma B are actually also in L. This is the case for the guarded negation fragment, and so for strong guarded negation separability, we obtain that it's 2x time complete. Now for the guarded fragment, well, those formula are in the guarded fragment for guarded fragment ontologies, but guarded fragment doesn't have the correct interpolation property. So we use a result that we have proven in parallel work, namely that interpolant existence in the guarded fragment is 3x time complete, and this lifts to strong separability. So also strong separability in the guarded fragment is 3x time complete. For ALCI, it's slightly different. So ALCI does enjoy the correct interpolation property, but the formulas are not in ALCI. Still, we could show that it's in 2x time and 2x time complete. So let me wrap up. So we have studied the impact of the signature of an additional signature restrictions to the separability problem. And what I find quite remarkable is those connections that we established, namely to conservative extensions for weak separability and to correct interpolations for strong separability. And yeah, as future work, we would like to look at other logics that we haven't been looking at so far. And also we want to look at the computation problem and the size of separating formulas, because in the end you are interested in actually getting those separating formulas. Okay, thank you, that's it. And I'm ready for questions now.